The good news is tonight's video is pretty short. It's less than 10 minutes. What? Fun. Okay. How did we feel about adding some more parent graphs in there? Did you guys notice the repetition is starting? You're like, I've been here before. It's the same but different. Slightly different things. So the nice thing too is I have graded the page of the test that corresponded to this stuff. And the page of the test that corresponded to this stuff went very well for most of you, which is good news because what typically ends up happening is what happened with you guys. These questions tend to be like the gimme problems on tests, where I get to that page of the test and it is 100% for almost everybody, and that's like the problems that like pad your grade, which is nice. So that seemed to work out on the test that I just graded, is that like when I got to the stuff on characteristics, it was like, yep, full credit, full credit, full credit, full credit for most of the points. And then it might be like somebody got like the increasing answer wrong, or somebody got like somebody might have gotten something wrong here or there, but for the most part, you guys seem to get it, which was great. So for these ones, we have a little bit of funkiness here and there, which is kind of how it starts to go from here on as we start to do different parent functions. There are parts that get a little bit weird. But I think that it goes, you guys have done the hard part where we learned it for the very first time. At this point, the funkiness gets introduced a little bit at a time. Does that make sense? So I think at this point, you guys have already done the overwhelming thing. Now it will be like, oh, this again. Now we get into the tedium. Does that make sense? Okay. All right, so we are going to example 2. So for this, we just have to figure out what chart we are using so that we can transform those points to draw the graph. So what parent function is this? Cubic, and how do you know? Yeah, it's got the cubed. It's the exponent of 3 that tells us. And so if we look at the chart that we are using is from the cubic. Do you have to memorize these? Are you texting me the chart? Why is your phone out? That's a great question. Okay, let's put that away, like all the way away so you're not tempted. Marvelous. Okay, so you don't have to memorize the chart. What should you do if you don't have the chart memorized and you have a cubic graph randomly on an assignment? You could get your notes out, or what else could you do? You could plug in -2. Yeah, take the parent function, x to the third, plug in -2, plug in -1, plug in 0, plug in 1, plug in 2, and then you have your chart. You have your numbers, okay? All right, so let's go ahead and take all those points. And we're going to do each one of the transformations on those points, which means we need to know what the transformations are. So from the equation, can you guys tell me what are the transformations? Okay. Right 1, up 5, okay. We don't call it a vertex because a vertex means it's supposed to switch from increasing and decreasing, and these graphs don't switch. They either consistently go up or consistently go down. So we're going to call it a locator point. What is the locator point for this graph? 1, 5. Okay. All right. So when we do that vertical compression of 1/2, does that happen to the x-coordinate or does it happen to the y-coordinate? The y. So what are we going to do to the y-coordinate? Yeah, multiply by 1/2 or cut it in half or divide it by 2. So -2, -4, -1, -1/2, or you could do 0.5 if you want. 0, 0, 1, 1/2, or you could do 0.5 if you want. 2, 4. So fractions are fine, decimals are fine. It depends on your preference. Okay. All right, and then we're going to go ahead and do right 1. So -1, 0, 1, 2, 3. Okay. And then we are going to do up 5. So -4 up 5 is the easy one. -1/2 up 5 is 4.5 or 4.5. Up 5 is 5. 1/2 up 5, 5.5. And then 4 going up 5 is 9. Okay. So we've got -1, 1, 0, 4.5, +1, 5, 2, 5.5, 3, 9. And how do we draw this graph so that the curvature of the graph looks correct? All I've seen is T-Rex hands. Then you go middle. T-Rex hands middle. So half a parabola going up, half a parabola going down. I do like the T-Rex hands though. They were very amusing. They were like this, okay? It's like your elbows were fused at your sides. All right. How do your brains feel about that? Good? Okay. All right, so here we have a cube root. The cube root table is a little bit weird if you forget it because you don't just plug in -2 to +2. You want to think about numbers that are easy to cube root. 2 is not easy to cube root because if you cube root 2, you get a decimal, and that decimal is not very easy to graph. So when we think about numbers that we want to cube root, we want to picture numbers that are easy to cube root. Numbers that are easy to cube root are numbers like 64, 27, 8, 1. Remember when we were doing factoring cubes? You guys remember that? Sum and difference of cubes? We want perfect cubes to cube root in our table. So we use 1 and 8 because those are the very smallest cubes that we can work with. So for our table, I'm going to use -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. All right, what transformations do you guys see in that equation? I'm saying vertical stretch because in pre-cal you learn about horizontal stretches and compressions. So we're getting a good habit now by saying vertical. What else do we have? Grade 6. Up to, all right, what's the locator point? +6, +2, right? Okay, so that vertical stretch of 4, does it affect the x-coordinate or the y-coordinate? Y, and what do we do to the y? Multiply by 4. -8, -8, -1, -4. So if you guys notice, I have not yet given you an assessment where I took the calculator away. So I've given you assessments where technically if you wanted to, you could have graphed on a calculator. A lot of you guys have chosen to graph by hand, which is not a bad idea. But I have given you guys calculators on those. It is coming up where I'm going to give you an assessment where I take the calculator away and you are forced to graph by hand. Okay, I'm just letting you know that is coming. I put a 2 there because I was not focused on what I was doing. But I did want to let you guys know that is coming. Okay, so for those of you who were not graphing by hand, those of you who are using the calculator to help you graph, I want you to make sure that if you don't understand this method that you are asking questions so that you can graph without the calculator. All right. So we got the vertical stretch by 4. Go ahead and do the right 6 and the up 2. right 6, right 6, Miss Rice didn't even leave us enough space on the graph. Up 2. You guys see that vertical stretch of 4 happening? This is a very stretched graph. Okay, and then again, I've got the parabola each way, but it's like a sideways parabola this time. So half a parabola on this side, going this way sideways, and then the other half going this way sideways. Ta-da! Okay. Do you guys have any questions about any of the other things that were in the video notes? Was there anything that was weird that you would like me to explain in person? How do we feel about the mountaintops and valleys for max and min? Did that make sense? So for something to have a maximum, you have to have a high point. You got to see the graph go up and come back down. It's got to have a little mountaintop for there to be a maximum there. If you think about the 3 graphs that we added today, we added square root graph. Does that have a mountaintop or a valley? Nope. We added cubic graphs that look like this. Does that have a mountaintop or valley? Nope. We added cube root graphs that look like, that was terrible. We added cube root graphs that look, there we go, like this. Does that have a mountaintop or valley? Nope. So when we have these graphs, the ones that we added, it's going to be none, 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 none. So the only time you're going to have an answer for maximum or minimum today is if I happen to throw in a parabola, a quadratic, or an absolute value graph into the packet to say, hey, do you still remember these from last unit? Okay. Otherwise, if I ask about maximum or minimum based off the 3 graphs from the video notes, you're going to say none for both of these because the 3 graphs I introduced do not have them, no matter what the transformations are. Increasing, decreasing interval, how do we feel about those? We feel okay about those? What if I was to take this exact example right here, example 5, and instead of asking about the increasing and decreasing interval, what if I asked about the domain and the range? Let's go ahead and do that for this example. Domain and range for example 5. So we have that locator point 3, 6. You're going to notice that that locator point is really important for the square root graph in particular for helping you find the domain and range. So the domain is the x values. If you forget, we got the posters on the wall. X values. So domain is how far left does the graph go, how far right does the graph go. Your locator point is 3, 6. So how far left does this graph go? 3. Can you put your finger on the 3? Yes, so bracket or parenthesis. Okay. How far right does the graph go? Infinity. Okay, so the domain of this graph is 3 to infinity. We found the domain visually because visually is the easiest way to find domain. But what that literally means is that if you were to look at what numbers are you allowed to plug in, the very smallest number that you can plug in is 3. If you tried to plug in a 2, what would happen? What happens if you plug in 2 for x? 2 minus 3 is -1. Are you allowed to have a negative under a square root? No, you get an I, right? And an I is a fake number. So you can do it, but technically it's fake. You get that? Huh? You can't graph imaginary numbers. We can't graph them in the real sense. There's an imaginary, but that's like a whole nother math. Okay. So when we look for the domain, we're looking for real numbers. Where are the real answers at? The real answers are for 3 to infinity. Okay. When we look at range, we're looking for down to up. So how far down does this graph go? Not infinity, but you're close. Negative infinity, because that's an arrow going down, so it's a negative. Negative infinity. How far up does the graph go? 6. Yep, it's that y coordinate of the locator point. Now, I can put my finger on that, so is that a bracket or a parenthesis? Bracket. Perfect. Okay, let's hop back up to example 4. Let's find the increasing and decreasing intervals for example 4. If you put a stick figure right here, and that stick figure started walking, let's come up with an imaginary tale for what that stick figure is doing. It's like that stick figure is like taking a hike, and it's like a steep hill, right? That stick figure is doing a steep hill. And then what happens right here? It's like climbing like a rock wall or something, right? So we're saying, so what is the stick figure doing? Increasing or decreasing? Increasing. Okay. If you climb a rock wall, would you call that increasing or decreasing? I would still call that increasing. Okay. Now you get over the rock wall, and then what are you still doing? Increasing. So even though the slant has changed, what happened the entire time? You were increasing that entire time. Does that make sense? We are in America. We go left to right. America. America. All right. What is this x value? Okay. And then what is this x value? Okay. And so what is our answer for increasing? Okay. And so based on the picture, what's our answer for decreasing? None. Okay, so I just want you guys to understand that it is possible to say that the stick figure was increasing the entire time. Even though you can see that things clearly changed in the picture, it was still increasing. It was just a different type of increasing. You were increasing at a different rate. Does that make sense? So you're increasing like, oh, it's like kind of slow and steady increasing, and then like, whoa, rock wall, and then, you know, slow and steady again. Does that make sense? Yes, Miss Rice. Marvelous. Okay. Any questions about this page? Are we okay with x-intercepts, y-intercepts? Do we try that again on our calculator? Can we do that today? I think this is what we really struggled with before, the calculator stuff. Desmos was cool. We got to click on it. But with the calculator, we had different instructions, and that was a little bit more difficult. End behavior, this is where it got funky. How do you guys feel about writing undefined? Did that make sense? There was no left arrow. There was no left arrow, so when I say, what is the left arrow doing? You're like, that's a dumb question. It's doing nothing. It's not even there. So we write undefined because it's not there at all. Okay. So I've got an assignment for you. You're going to be like, whoa, this is deja vu. I feel like I've seen this assignment before, just with different problems, different numbers. That's how you're going to feel again today.